Welcome to Statistics in Excel video number 89. Hey, if you want to download this workbook and follow along, click on my YouTube channel, then click on my college website link, and you can download the workbook Business 210 Chapter 9. Here we're in Chapter 9, Hypothesis Tests. And we want to go over to our PDFs and talk about hypothesis testing steps 1 to 5. Now, in our last video, we compared confidence intervals and hypothesis testing. That was a particular example of hypothesis testing when we had two tails. All right, we're going to go through all the steps, and then we're going to do the example in Excel. Hypothesis testing, one sample for this chapter. What is the hypothesis? A statement about the population parameter subject to verification. A statement about the value of the population parameter developed for the purpose of testing. Now, hypothesis testing, a procedure based on sample evidence and probability theory to determine whether the hypothesis is a reasonable statement. Not whether it's true or not. Because of our alpha risk, we can never say the original statement is true. We can say whether it's reasonable or not. We always have a little risk that maybe it's not true. If we make our alpha really, really small, then we're pretty sure that it's 99.9% close to true, or 6, 7, 8 standard deviation close to true. But we can never say for 100% sure unless we test the whole population that it is true. Hypothesis testing. Hypothesis testing does not prove that the hypothesis is true, but rather determines whether the hypothesis is a reasonable statement. All right, the steps. We talked about this last video, but here they are officially. We first develop the null and the alternative hypothesis. Now, as I mentioned before, we could see H sub 1 for alternative or H sub A for alternative. The null hypothesis will always be H sub 0, no difference. Then we specify the level of significance. That's the risk that if we were to reject the null hypothesis, that it is actually true. Third, then we collect sample data and compute the value of the test statistic, either z, if we're testing about a population mean and we know the standard deviation of population, we use z. If we're doing proportions, we use z. If we're testing a mean, but we don't know the population standard deviation, we use t. Step 3, I always like to draw a picture too. It certainly helps me. And then we have two approaches, either the p-value or the critical value approach. Use value of the test statistic to compute p. So we have some z, and that helps us calculate a p. To go from z to a probability, which will be p, we use the NORMSDIST or the t-dist. And then from that p-value, we can reject h sub 0 when p-value is less than or equal to alpha. The critical value approach, we use the level of significance to determine the critical value. Really, we just look at our risk on a chart, and whatever the dividing point is between confidence interval, or if you're doing two-tail, or the non-reject region and the reject region, will be our critical value. And in step 4, we not only determine the critical value, but we state the rejection rule. And that'll be different each time depending on our critical value. Whereas with p, the rule is just going to be straight. It's the same every time, whether it's two-tail, one tail to the left, one tail to the right. Back to the critical value. Step 4, we calculate the critical value, state our rejection rule. And then step 5, use the value of the test statistic and the rejection rule to determine whether to reject h sub 0. I'm not going to read this one. This is just the confidence interval approach to hypothesis testing, which we saw last video. Now, the next couple pages here in the PDFs can be helpful because I kind of put all of the formulas and Excel formulas and statistics formulas together. Here's our test statistic, either z or t. our critical value, that is going to be the dividing point between the region where the null hypothesis is rejected and the region where it is not rejected. We saw this in the last video. We have some dividing point. Those are our critical values. Last chapter, those were called confidence intervals. But in this chapter, we're not limited to a two-tail. We can have a one-tail on the right or the upper end, or one-tail on the left or the upper end. Whatever that value, that z is, that divides it. Reject the original statement. Don't reject the original statement. Now, next slide. This is for the proportion. We've already done this a few different chapters. But there's our z. Don't forget that you must verify all of the four elements that make a binomial test, and then test these two things to see whether you can use the normal distribution. These next two pages, Excel functions, I show you all the situations for each one of the types of tests and what kind of formula you could use. Same with the t, when sigma is not known. Very important sheets. Our next video, I'll actually go through and just show you how to use, just show you a video just on the functions without talking about all the hypothesis testing. Now, I want to move on to an example and go through the 5 steps for hypothesis testing. Here's our example. We have a statement from an official report. The yearly salary earned by full-time realtors is $85,000. And it also says that there's a sigma of 12,549. Okay, so that's the original statement. Now we have a researcher that believes realtors make more than $85,000. So there's 2 competing statements. Now again, if we were to take a sample and get 88,595, right? There's a huge difference between what the original claim was and what our sample x bar is. That difference is called sampling error. And our job is to find out if it is a true difference, which would mean statistically significant, or some small sampling error that's not statistically significant. We want to talk about step 1, the null hypothesis and alternative. Now, H sub 0 means there's no difference from the original statement. Alternative hypothesis, you've got to be careful with me, because there's a couple different ways to write notation for the alternative hypothesis. It could be H sub A or H sub 1. Notice we have a 0 here, so one way is to just call this a 1. The other way is to call this as alternative. So, and I go back and forth between these. Okay, more about step 1, the null hypothesis. A statement about the value of the population parameter developed for the purpose of testing numerical evidence. It's going to be assumed to be true from the beginning. However, we cannot conclude definitively ever that it is true because of our small amount of risk. The only way we could say this is true, do the whole population, whatever tests we're doing. Alternative hypothesis, that's supposed to be a little 1 there, sub 1 or sub A. Statement that is accepted if the sample data provides sufficient evidence that the null hypothesis is not reasonable. In essence, we will accept this alternative hypothesis if we reject H sub 0. Now, how do we set up these two hypotheses? Let's go to our next page. I'm going to scroll down here. I have a little diagram here that will help us. Now, the original statement was a researcher thought that the mean was greater than 85,000. So the trick is to look at whatever the question is, or and select that for the alternative. So always write H sub 1 or H sub A first. So this person thought that the mu was greater than 85,000. So you just draw that greater than symbol right there, and you do H sub A or 1 colon mu and the 85,000. And then the only tricky part is this. And in last video we saw how we actually did write all of this other stuff first, and we just left the operators empty, and we looked at the question and then filled these in second after writing the details on either end. So this operator, this comparative operator, comes from the researcher statement, and we say greater than. Then, once you have this one, it's pretty much done. Here's why. Because you just take this, flip it around, so the less than is that way, and the equal sign always goes in the null hypothesis, the original statement. So that really is the trick that helps you set up null and alternative. Now let's talk a little bit more about the possibilities for null and alternative hypothesis. We could have a research hypothesis. If you do, like we do in this case, as we said, the H sub 1 or H sub a, that automatically goes to the alternative. So whatever the researcher is thinking goes into the alternative hypothesis. And then you do this one second. So in this case, does the process take less than 30 minutes? So if you had a piece of equipment and the old equipment did 30 minutes and you want to make some improvements, that would be your question. Does the new process take less than 30 minutes? So that would be your alternative. So when you have a research question, it almost always, that question goes to the alternative first, and then you fill this one in second. Now, validity of a claim, that's another possible setup that you might get. The claim is usually given H sub 0. Now here's an example. Is the ketchup bottle filled with 16 ounces? Now I'm going to throw you a loop here and give you two different examples from two different points of view. So the original claim is the bottle is filled with 16 ounces. Now imagine if you are a consumer. You see 16 ounces in an ad or on the label, right? Now consumer only cares if they get 16 ounces or more. That's all they care about. What it would bother them is if it was less. So this is the mu, the population mean. If the mu was less than 16 ounces, statistically significantly less, that's what they would care about. So the original statement here is that it was filled with 16 ounces. Since the point of view of the consumer is less than, you've put this one first, you jump up here, put the equal sign and a greater than. But this is really the original claim, 16 ounces, yes. Now what about the same situation, but from a manufacturer's point of view, where they have a filling machine, right? Manufacturer cares if it is filled too much or too little. So really, validity of a claim, the machine is filling 16 ounces. In this case, we do equal to, right? And the alternative would be not equal to. Now technically, the way this textbook sets this one up here is that this is a decision making. And it really is, because if we run our experiment and the null hypothesis is that it's equal 16 ounces and we do not reject this, hey, that means the machine is filling the bottle properly and we don't shut down and fix it. But what if we reject this one and accept this one? The decision is then to shut down the machine and fix it. And this happens all the time around the planet Earth with all sorts of manufacturing. So really that's a manufacturing one. But I put that one up here because this question right here depends on what point of view you're coming from and how you set up null and alternative. Decision making, another example. Should we accept a box of 20-meter boomerangs? Well, if it really matters whether the boomerangs are 20 meters or not, for example, in competition, if you have a boomerang that goes too far for some of the speed events, you wouldn't want it. If you had a boomerang that went too short, then you couldn't even use it in the event. So if you get a big shipment, you might have to test them to make some decision, right? If they fly too short, can't be used in competition. If they fly too long, then the times will not be fast enough. So really the question is, do we accept the shipment of 20-meter boomerangs, or do we reject it and send it back? And so if you get lots and lots of boxes, you're not going to test them all. You're going to do some sample. So decision making usually gets this two-tail like this, equal to or not equal to. That's just a little bit about setting up the null and alternative hypothesis. Let's go to step 2. Select a level of significance. Now, as we talked about in last chapter, we talked about level of confidence. 1 minus whatever the level of confidence or the confidence coefficient, that will give you our alpha. Alpha, or level of significance, is the probability of rejecting the null hypothesis when it is actually true. One way to think about it is innocent but found guilty. So right in our court system, right? You were innocent but found guilty. That means that the null hypothesis that you were innocent, you were found guilty, right? So we accepted the alternative hypothesis. And in our legal system, the null hypothesis is always that you are innocent, right? If we can prove then that to find you guilty, then that would be the alternative hypothesis. So that's one way that I used to when I was learning this, to remember. My great statistics teacher at College of Alameda, Dr. Payne, gave that to us, and it just helps tremendously remembering what alpha meant. Here are some levels, standards for levels of significance. In quality assurance, they usually stick to 0.01. Consumer research, maybe 0.05. In politics, maybe 0.10. Anything greater than this, and it doesn't provide basically much evidence at all for rejecting. Here's our example 5, our real estate example, right? We chose alpha equals 0.5. So we're taking a 5% risk of rejecting h sub 0, even though it could be true. Here's a picture, right? Oh, here's our upper tail, our one tail to the right. The whole alpha, the whole risk goes up here. That will be our dividing point. Anything over here, we don't reject. Anything above, we would reject the null hypothesis and accept the alternative. There is the null and the alternative. All right, here's some pictures for step 2, just to help you out. 0.1, we divide, put 0.5 there and there. This is on the low end or the left. This is on the upper end. What if we had 0.5? Then this would be alpha divided by 2. That's actually should be alpha divided by 2. 0.25, and then see alpha. This should be alpha divided by 2 right there too. Otherwise, we just put the whole alpha in the tail. For 0.01, we have 0.5% or 0.005 here and here. Again, that's actually alpha divided by 2. Otherwise, we just put the whole alpha either in the low end or the upper end. And then there's some examples of what the null and alternative hypothesis might look like for our $85,000 example. All right, also alpha. Let's talk about alpha and beta. There's alpha, there's beta. Because there's a certain type of error that in statistics that we need to talk about. And type 1 is alpha. Type 2 is beta. Now here's the population condition. We have h sub 0 true, or h sub 1 is true. Now remember, we never know for certain whether something's true unless we test the whole population. Now here's our conclusion, right? We can only come to 2 conclusions. We either accept h sub 0 or we reject h sub 0, which in that case means we'd accept h sub 1. Here's a little table. And let's look at what happens when h sub 0 is true. Accept h sub 0. Oh, then we come to correct conclusion, right? These are our conclusions. But what if we reject it, right? So h sub 0 was true. You were innocent, but they found you guilty. That's called alpha or type 1 error. Now, let's look what happens not if h sub 0 was true, but h sub 1 was true. If we accept h sub 0, we get a type 2 error or beta. That means we accepted it even though the alternative was true. Now, what if still under this h sub 1 is true, or h sub a is true? What if we reject h sub 0? Oh, then we get the correct conclusion. Now, why does this matter here? It matters for us because pretty much all we're going to be doing is type 1 alpha. So our type 1 error is h sub 0 is true, but we reject it. We're going to be able to control this by picking our alpha level, our level of significance. So we have some control over this. And that is the reasons why we're going to, when we make a conclusion, why we're going to be able to accept h sub 1 in essence as being true. Because we're not controlling for beta, we're never going to say except h sub 0. In our last video, you saw we made some conclusions, but we never said h sub 0 was true. What we said was fail to reject. Fail to reject h sub 0. And the reason why is because we're not controlling for this beta right here. We are, by our ability to select the significance level, controlling for alpha or type 1. So we will be able to say accept h sub 1. That's an important point. So for us, there's only two conclusions are possible. We either fail to reject h sub 0, or we reject h sub 0 and accept h sub 1 or h sub a. So those are our only two conclusions. And we'll be careful in our language. I tend to always say something is reasonable or it's not reasonable. Or maybe I say something is, this is extremely reasonable given our sample evidence. Or this is not reasonable, or this is extremely unreasonable given our sample evidence. All right. I think we're going to go over to step 3. Step 3, that's where we're going to collect data, calculate our test statistic, draw our picture. And here for our real estate example, there's the line right there. We got our alpha there, the rest of the probabilities there, and we will calculate our critical value. And we'll do that in just a moment using our norm S inverse. And there it is. You use norm S inverse to get your critical value. And then next, we're going to state. All right, got to draw that picture. I'll draw this here. This is our rejection region. Reject h sub 0, accept h sub 1. Over here, fail to reject. And then we write our decision rule or rejection rule. If our calculated test statistic is greater than 0.645 in our case, we reject h sub 0 and accept h sub 1. Otherwise, we fail to reject. Nice, straightforward. You could basically always use this for and just change the numbers depending on what your critical value is. And then in the case of concluding, we are going to, when we do this example, we'll calculate. There's our 88,595 minus our 85,000. There's our standard error. We calculate a z. So there's for this value right here, 88,559, that's our sample mean. We got a z, which is number of standard deviations above, of 1.72. So we make our decision. Because our calculated test statistic is greater than 1.645, we reject h sub 0 and accept h sub 1. It is reasonable to assume that the mean salary for real estate agents is greater than 85,000. And there's a picture. There's our hurdle, right? Critical value. There's our test statistic. Now, that is using critical value. For p-value, you would go ahead and calculate our p-value right here. That would be 0.04282. We can visually see that it is less. So the probability of getting this value or more is much smaller than the risk we're willing to take. So that's an automatic rejection. Even though we have our critical value there, you don't need it when using p-value. And there's how we'd calculate our p-value for this one. It's on the upper end, so we had to do 1 minus and the NORMSDIST, because the NORMSDIST gives us the probability. And there's the probability. Now, something interesting about this p-value. The rejection rule is always going to be whatever the p-value we calculate. Is it less than or equal to our alpha? For a left, this is our left test, right? Here's the risk, the alpha, and there's our p. So in our case, we reject because it's smaller. But notice this rule, is p-value less than alpha? If it is, we reject. What about on the upper end right here? There's our alpha, and there's our p-value. For this example, I just drew pictures, so the p is less, so we reject. But look at this. The decision rule or rejection rule is the same. P-value less than or equal to alpha, reject. The only tricky part, and we saw this in our last video, is when you get a two-tail, right? You have to divide alpha by 2. So alpha divided by 2 is here and here. And whatever p-value we calculate, it's going to be on one side. So in this case, for this example, we calculate 0.0075. You actually have to multiply it by 2. The reason, well, visually you can see, is this less than this half? Yeah, it is. So we automatically reject. But to have just one rule, it's always, is p-value less than or equal to alpha, then reject, right? That means when you get to two-tail, you got to remember, when you calculate that p-value, because we have some test statistic here or here, calculate the p-value and multiply it by 2. That way we can have a universal rule, which is the total p-value, whether it's one-tail or two-tail. Is it less than or equal to alpha? Then reject. All right. Here's a summary picture for both critical value and p-value for our case with our formulas for calculating them. All right, now I want to go over to Excel, and I want to actually do this problem. Here it is. A statement from an official report said the realtor makes $85,000 a year. Researcher thinks that the realtor will make more than $85,000. Alpha equals 0.5, sigma, and n. Can we conclude that the realtors make more than $85,000? As soon as I see that, or as soon as I do the researcher, I see the researcher's question, in step 1, I jump to the alternative hypothesis. And I'm going to do our little trick here. I'm going to say H1 space colon, and then I'm going to come back here, and I'm going to do right-click, format cells, and do subscript. Right? So there is our alternative. I'm also going to list it here just because I know as you're learning this, it may be confusing that we use different variables. But there it is. Either one you want. So we have our alternative colon. We're going to save the operator, the comparative operator. We're going to immediately, I'm sorry, here we're going to put mu. We're going to save the comparative operator, and we're going to immediately come here. And the original amount was $85,000. And this was in dollars. So I'm actually going to format this with a currency. Now watch this. If I can make this a little bit smaller here, I'm going to copy this up here like this. Change this to 85,000. I don't want that. This is not the. This is the original mu. This is the hypothesized mu right here. So I have a mu, and I'm going to change that one to 0. You can type all that out. That was all silly that I copied that. But the point is, you put all this there, this all there, mu, amount. Later, when we do p, we'll put p population proportion, and whatever the proportion is, same thing. And then it's just the operators that make the null and alternative hypothesis different. Now, the trick is to take whatever the researcher's statement is. Can we conclude the realtors make more? So that means we put this operator here. Is mu is greater than 85,000. Then we immediately come up here, put the opposite, which is less than, and always put the equal sign. Right? So step 1. We've done step 1. There's our null and alternative. Now, we were given a standard deviation of 12,549. Let's see if I can make this the right size here. OK, and the hypothesized mu, that's h mu sub 0, that's our 85,000 here. And it came from some official report. And since it's an official report, we're going to assume that that is the population mean, the hypothesized mu. Now, alpha, we're told that it was 0.05. Now, do I even need to calculate alpha divided by 2 here? Here's another great trick for hypothesis testing. You can tell from this operator here whether it's a one tail to the right, one tail to the right, one tail to the left, or two tail. If it says not, you know it's a two tail. Is this pointing over here? So that means it's always going to be, we're testing on the upper end, So we don't need this. If we were to do our chart, it would be, that picture and just a little. In fact, we just saw the picture just a moment ago. So we can skip over that type of test. This is going to be one tail test on the upper end or the right. Sample size, 36. Sample mean, 8,595. Now, hey, watch this. Notice there's a comma there. When I Control Enter, notice there's no comma there. That's called formatting as you type. That number gets stored. That's just like a number formatting. All right, we have our input data. Now we can calculate our values. We need standard error equals, and we'll take our sigma divided by square root of our n, standard deviation for the distribution of sample means. And now let's do two methods, critical value, and then we'll do our p-value. So our critical value, we're going to calculate that first. That is the marking point between reject and not reject original statement. We're going to do equals, and we're basing critical value off of alpha. So it's norm S inverse, and it's asking for the probability. This is on the upper end, so we can't use 0.5. We need 95, so we do 1 minus that. All right, once we calculate that, we can state our rejection rule for critical value. If our test statistic is greater than or equal to our critical value, we reject h sub 0 and accept h sub a. Otherwise, we fail to reject h sub 0. If our test statistic is greater than 1.65 rounded, reject h sub 0 and accept h sub a. So we need to calculate our test statistic. And what is our test statistic? It's sampling error divided by our standard deviation or standard error. That'll tell us our z, how many standard deviations above or below the mean we are. So equals open parentheses x bar minus our hypothesized mu divided by our standard deviation. And boom, we get 1.71. That is greater than our critical value, our hurdle point. Our rule tells us that we must reject h sub 0 and accept h sub a. And here is our conclusion. This is the critical value conclusion. Because 1.72 is greater than 1.64, we reject h sub 0 and accept h sub a. From our sample evidence, it is more than reasonable to say that the mean annual salary for realtors is greater than $85,000. Now, we calculated our test statistics, compared it to our critical value. Rejection rule came to a conclusion. Now, for p, our second method, that was step 4 and 5 for critical value. For p, we calculate our test statistic. Remember, that sits on, I don't have the pictures over. Here's the PDFs. Here's our picture. There's our critical value. There's our calculated test statistic. The p-value will involve the probability. So if we got the probability from there to there, it will tell us the likelihood of getting that particular value or greater. So we'll go back to Excel. We have our test statistic. We come down here and to do the p-value, which is the probability. We do norm S dist. So equals norm S and dist. It says, hey, you give me a z, and I'll give you a probability. But what does it do? If I give it 1.72, if we were to go look at our picture, it'd give everything from way over here up to there. And since we want only all the way up to there, so since we want the top, we have to 1 minus. When you get these, that means you have a slight error. It looks like I forgot a parentheses. You basically never want to click yes, even if it's looks correct, especially when you do bigger formulas, it's almost never right. So you click no. It's kind of like spell check is wrong a lot. And then I'm going to look through it, and then I see that I left the parentheses off. Oh, and it's less than our 0.5. Of course, it has to be, because we saw our test statistic compared to our critical value. So our conclusion for p-value, because 0.0428 is less than 0.5, we reject h sub 0 and accept h sub a. We get the same exact conclusion. It is more than reasonable to say that the mean annual salary for realtors is greater than 85,000. Now I want you to notice something. The rejection or our conclusion, notice we said because 1.72 is greater than 1.64. See that? Greater than that one we rejected. But look at our conclusion here, because 0.0428 is less than 0.05. Yeah, if we draw a picture there, the probability, right? Visually, we know that probability is smaller than the alpha, right? So we really have less than, if our p-value is less than our alpha, we reject. But for on this upper tail test, if our test statistic is greater than our critical value. So that's just an important thing to realize. When you're doing critical value, we get a value greater than, we reject. When we're doing probability and we get a p-value smaller than our alpha, then we reject. All right, when we come back in our next video, I'm going to talk about the functions, in particular the t functions. We got to kind of get used to because we're going to use them a lot in this chapter. And then we'll have a few more examples for hypothesis testing. All right, see you next video.